In this tutorial we'll be investigating more to do with using interrupts in a circuit. But before we do that, we'll do it the old-fashioned way with some polling. For this first question, we've got a series of digital pulses fed into a microcontroller on P1.5. We need to set up this port as an input and the other as an output. So P1 dir is equal to 0xdf. Alternately, we could have said something like P1 dir is equal to bit 5, and we put a not there, so that one will be low and all the other ones will be high. Our second question, what we want to do is count the number of pulses received by P1.5. So essentially we're looking for these low to high transitions, and we want to increment a variable called counter, and we're assuming no debouncing. So let's declare counter, int counter equals 0, so we initialize it properly. Then we have our infinite loop, so while 1 and we've been asked to draw a flow diagram as well. So essentially what we want to say is something like if P1.5 equals high, if that's not true, so it equals low, we'll go back around to the start now. If it is true, we want to increment our counter. Then we want to say, well, is it still equal to 5? So this will allow us to have that transition from low to high. So if P1.5 equals high, if that's true, we stay back here. If it's not true, we'll go here and wait for it to equal high again. Once it equals high again, we'll increment our counter again. So let's have those conditions. Firstly, while 0 is equal to P1 in and bit 5, we're going to wait, so that implements this part of it here. When it's not true, when it equals 1, we'll come down to our count condition. So we say counter plus plus, do our count, and then we have another while loop, while 0, in this case we're looping if it's true, so we want to say if it's not equal to 0. And we keep on looping around there. So that code now reflects our flow diagram. So our next question firstly asks, why might this be inefficient? And we can say, well, we're basically spending all our time polling, and in this time we could actually be doing something useful. So now we're going to write that version in an interrupt implementation. So same functionality as question 2, but we need to use interrupts instead. So let's start off with writing our main function. So we have void main void so we'll have our main code here. So we want to set up pin 5 as an input, so that was basically our first line of code. P1 in P1 dir is equal to 0xdf as before. We want to enable interrupts for pin 5 then, so we're unmasking that one. P5 interrupt enable equals bit 5. We then need to say positive edge triggered, because we're using a positive edge triggered interrupt. So we say P1 interrupt edge select register, and we'll set that to 0, because if we set bit 5 to 0, it's positive edge triggered. If we set it to 1, it's negative edge triggered. We'll just put a few comments there. And then we'll set the flags P1 IFG. We'll clear them, so we're setting them to 0. And we're going to enable interrupts, so we use the EINT command. Then we can have a tight loop, so we say while 1, and we've set up interrupts. That should actually do everything for us. So all the counting won't be done in the main loop, it will be done outside of that in our interrupts. So now we need to write our interrupt service routine. So just like in the lectures, we start off with pragma. It's a compiler directive, and in this case we're saying the vector that we'll be using is equal to the port 1 vector. We then need to write our interrupt, so we start off with double underscore and we say interrupt. Now we have no return value, so we say void. We have, we'll call it pulse counter for example. And we have no parameter that we pass to it, so we say void. And inside there we just want to increment our count plus plus, and we want to clear our interrupt flags. So P1 IFG is equal to 0. The only other thing that we should mention is that we should have declared our counter to begin with, and the counter will be a global variable, so we'll declare it up here somewhere. And we should declare it because we're using it in our interrupts as a static volatile. So static volatile int counter. Okay, this last question, we're just writing the interrupt service routine, so we'll assume everything's been set up for us. And what we want to do is we've got 4 different buttons on P1.0 through to P1.3. When any of these are pressed, a corresponding LED on P1.4 to P1.7 is updated. So if we press P1.2, we turn on LED on P1.6 and so on. So we could have a bunch of if statements inside here and check each of the different pins or each of the different bits of the P1 IFG register. that will actually work. If the bits are high, that's the one that actually triggered the interrupt. But we're going to do it slightly differently. So what I'll do, I'll get a character. So the P1 IFG registers only 8 bits. And we'll store our switch values in there. Now what we'll do, we'll shift that up 4 times. So that it lines up with the LEDs. So our switches are on P1.0 through the 4. So these ones are our switches here. These ones are our LEDs here. What we're going to do is we're going to shift this 3 times to the left, and this bit here will now line up with this one, and this one will line up with this one, and this one with that one, and that one with that one, so on. What we then need to do is invert these values. So we can use our tilde. Now we want to invert them, because if a particular interrupt's been triggered on P1 IFG, that bit in P1 IFG is going to be high. But we want to turn on the LED, and to turn on the LED we need to supply a low to that particular LED. We can then say P1 out is equal to our switch values. And we need to clear those flags again.